Good morning, dear students. Today we will solve a problem on boiling. Okay. So before proceeding to the problem, we'll just go through the correlations which we have discussed earlier. Okay. There are two types of correlations. We will see it in the data handbook also. So this is nucleate pool boiling correlation. Okay. This is also nucleate pool boiling correlation. This one is for finding out heat flux, whereas this one is for finding out critical or maximum heat flux. Okay, so critical point is where the heat transfer becomes maximum for the nucleate pool boiling, then it starts reducing because of formation of vapor film on the surface. Okay, then this one is for stable film boiling. In case of stable film boiling, as the temperature attained are very high, radiation will also come into picture. So we'll be calculating H convection, H radiation, then we'll be calculating the total heat transfer coefficient. Okay, note that all the properties are to be noted at T saturation temperature. So T saturation temperature will be for corresponding pressure. Okay, one more important point is that here it is 0.4, but in the data handbook it is 0.68. So we will be using 0.68 to solve the problems. Here, with respect to nucleate pool boiling, delta TE, which is excess temperature, it will be approximately around up till 50 degrees Celsius. We will be using nucleate pool boiling to solve the problems. For greater than 150 degrees Celsius, we will be using delta T greater than 150 degrees Celsius, we will be using film boiling formula. Okay, so now coming to the problem, water at atmospheric pressure is to be boiled in a polished copper pan which is 350 mm in dia and is kept at 120 degrees Celsius. Calculate the following. Here Tsat is given with respect to atmospheric pressure. So for atmospheric pressure, T saturation temperature is 100 degrees Celsius. So that should be noted down from the thermodynamic data handbook. Next, in this problem we have to calculate power of the burner, which is Q, then rate of evaporation, which is m dot, then critical flux. Okay, so I have to calculate both Q and Q max. Okay, now as we know that the problem is in nucleate pool boiling. Why it is in nucleate pool boiling? Because if I take the difference of the Ts and Tsat, which is 100, it will be 120 minus 100, 20 degrees Celsius. So now as per the criteria what we have set, it is in the nucleate pool boiling zone. So we will be using nucleate pool boiling formula. So we will be using first formula of this. We will be calculating Q by A, then we will be multiplying by the area. Okay. So we will get the value of Q. In order to calculate m dot, we will be using Q is equal to m into h of g. Okay. As m dot as it is in the vapor dome zone, so we have to use formula of Q is equal to m into h of g. We cannot use Q is equal to mCp delta T. We have discussed this in the previous class. So we will be using Q is equal to m dot into h of g. We get m dot also. Then in order to calculate critical heat flux, we will be using this formula. Okay. So with the help of these two formula, we will be calculating Q and Q max. Okay. If the problem given is in the range of 150 degrees Celsius, delta TE, then we can use this formula. Okay, you can see there is H convection, H radiation, and the combined heat transfer coefficient formula. And on this side you can see the notations used. So please go through all the notations so that you become comfortable. Okay. In this present example, there are certain formulae there are certain constants. You can see there is CSF and Cl. So here L indicates liquid property you have to refer. If it is specific heat, there will be two properties, one is for liquid, one is for vapor. Similarly, if it is density, one is for liquid, one is for vapor. If the subscript is L, we should be substituting liquid property. If the subscript is E, we should be substituting vapor property. Okay. So as we saw, the surface tension may also be required. So surface tension is here. You can see surface tension. So with this table we can note down surface tension. Okay. Even you can note down latent heat of vaporization from this page. It is given here. Or you can use thermodynamic data handbook. Then in this problem, the value of CSF is required, which is a constant. This constant is found out for combination water and the surface. So here it was a copper pan, so we'll be using this combination. For this combination, the value is 0.013. Okay. So there may be combination of water and platinum, water and brass. So accordingly, we have to note down the value of CSF. Okay. All these pages are there in the data handbook. So approximately it starts from 140. So around that range you can find out. So this is the page which will be providing you, or we have provided also. So please, using this page, you can note down all the properties which are required to solve the problem. So you can see here there is density value. Okay, density value for liquid as well as for vapor. Okay, now we can see I was talking about here with respect to temperature, the saturation pressure is given, but from the thermodynamic data handbook we can find out with corresponding to pressure the saturation temperature. Okay, even the value of HFC is also given, specific heat value is also given. You can see there are two things, liquid and vapor. As I told you earlier, liquid indicates L, okay, Cl and Cv. Thermodynamic conductivity is also given, Kl, okay, Kv. Dynamic viscosity is also given, which is mu L, mu V. Prandtl number is also given, and volume expansion beta. So beta is nothing but 1 upon beta is equals to 1 upon Tf. If required, we can use this. So what is that Tf? Tf is film temperature. Okay. Okay. Next, moving on to the data which is given is D is 0.35 meters, which is 350 mm. Ts is given. Tsat is given with respect to the atmospheric pressure. So you can note it down from the data handbook. Then Ts is greater than Tsat, and the value is excess temperature is 20 degrees Celsius. So it falls in the nucleate pool boiling. If this criteria, what we are verifying is, if this criteria is verified, then we say that water is boiling, because after 100 degrees Celsius for the corresponding pressure, the water will start boiling. Otherwise it will be it may not reach that saturation liquid point also. Okay, so as discussed earlier, all the properties should be noted at Tsat. So for Tsat, all the properties which are there in the formula are to be noted down. All the properties are noted down. You can see sigma, CSF, everything. Okay, continue. Once all the values are noted down, so you can see this is the first formula where all these values are required. Okay, so the value of N is 1 here. CSF is noted down for T saturation. All the properties are noted down at T saturation temperature in this present problem. And for further also, for nucleate pool boiling problems, we have to refer the T saturation temperature, Tsat, as the reference point in order to note down all the properties which are required to solve the problem. So all the values are substituted and the value of Q is calculated. Actually, we will get the value of Q by A. So by multiplying by the area which is calculated here, you can see actually we will get the value of q by a. After multiplying by this area, we will get the value of q. So why we have taken pi by 4 d square is, if you take a surface, a pan means the heat transfer is taking place perpendicular to the pan. So we have taken pi by 4 d square, pi by 4 d square. It is perpendicular to the surface. So heat transfer taking place perpendicular to the surface. So we take pi by 4 d square. Then m dot is q by h of g. So we get the value of m dot also. Okay, actually the formula is q is equal to m dot into h of g. By modifying, we are getting this formula. So in order to calculate critical or maximum heat flux, we are using this formula. After substitution, we will get the value of q as this much. So if you multiply by the area, we will be getting the value of q. But in the problem it is asked the value of critical heat flux, the value is calculated. And one more thing, that usually the value of q is always smaller than the value of critical heat. Okay, that means q by a is always smaller than q by a critical heat flux, q by a for critical heat flux. Okay, there is a similar problem. You can see problem number 2. Please you can try to solve it on your own. Okay, thank you.